In this video, we will do some review problems from AP Calculus Unit 3. We're going to do some derivatives, including implicit differentiation, but we will also find horizontal tangent lines and explore relative max and min. For problem number 1, we need to find the derivative of y equals 4 to the tangent x. But first, here's a little side note for you. If you have y equals a to the x power, where a is a constant, then y prime will be a to the x power natural log a. So this is exactly what we will do on this problem, but we will also have to use the chain rule because we've got this function inside of the function. But taking the derivative of the outer function, we will have y prime is equal to 4 tangent x, that's the a to the x part, times the natural log of 4, that's the natural log of a part. But now here comes the chain rule. We must multiply by the derivative of the inner function. So we multiply by secant squared. For problem number 2, we have to do the product rule because we have this yellow function times the blue function. So as I do y prime, I will first take the derivative of the yellow function. So the derivative of e to the x power is e to the x power. But we have to do the chain rule right now because we don't just have x, we have 2x. So we have to multiply by the derivative of the inner function 2x, and that's just 2. So this is the derivative of the yellow function, and we multiply that times the blue function unchanged. And then you put a plus sign, and you go through it again. But the second time through, you leave the yellow function unchanged. So I'm just going to put e to the 2x power. And then you multiply by the derivative of the blue function. The derivative of sine is cosine. Whoops. Cosine. And that's it. Now this is perfectly acceptable, but for a multiple choice question, you might see it written with the GCF factored out. We have this e to the 2x power in both terms. So you might see it with the e to the 2x power out in front of the parentheses, leaving behind 2 sine x plus cosine x. Time for some implicit differentiation. Before we get started, let's rewrite this as sine y to the 1/2 power. Now we're just going to take the derivative of each term, but remember we are taking the derivative with respect to x. So if we take the derivative and the variable is y, we're going to have to use the chain rule. So starting here with the outer function, the derivative of sine is cosine. So we have cosine y to the 1/2 power. But now the chain rule kicks in and we multiply by the derivative of this inner function. So we're going to put that 1/2 in the front. Reducing the exponent by 1 will give us negative 1/2. But actually we need to do the chain rule again. Because this is a y and not an x, this y is considered another inner function. So we have to multiply by the derivative of y. In other words, we multiply by dy dx. Now the derivative of cosine is negative sine. And the derivative of a constant is 0. For the rest of the problem, we're trying to get dy dx by itself. Let's start by adding sine x to both sides. Okay, so sine x is over here now. I made one other small change. Because I have this negative exponent, that told me to drop this factor down to the denominator. So that's why I have 1 over 2 y to the 1/2 power. I just dropped the y to the negative 1/2 power down to the denominator. So next I'm going to divide both sides by cosine y to the 1/2 power. So this is going to end up in the denominator right here. So far we have this. We need to get dy dx by itself. So we have to get rid of this fraction in the front. There are two ways to think about it. One way to think about it is we're going to divide both sides by this fraction so they will cancel out on the left-hand side. But then on the next step, we will multiply by the reciprocal. So you can see that the 2y to the 1/2 power is going to end up in the numerator. But there's another way to think about it. You can think of it as multiplying both sides of the equation by the reciprocal of this fraction. That way, these are going to cancel each other out and leave you with dy dx, and you will be left with all of this on the right-hand side. So we get this. I just went ahead and put the 2y to the 1/2 power in the front, so it would be super clear that this is not inside the sine function somehow. There is one more little cosmetic thing that we can do. This is a perfectly acceptable answer, but when we started out, we had a square root of y instead of y to the 1/2 power. So it might be nice to put this back as a square root again. And this is probably how you would find it if this were a multiple choice question. Problem number 4 is another implicit differentiation problem. So taking the derivative of the first term, I get negative 2x plus, and then I'm going to have to use the chain rule here, but for the outer function I have 2y, but then I have to multiply by the derivative of this inner function, which is simply dy dx. So again, anytime the variable is not the same as the variable with which you are taking the derivative, you have to use the chain rule. Anyway, the derivative of 1 is 0. Now we need to get dy dx by itself, so I'm adding 2x to both sides. So we have 2y times dy dx is equal to 2x. Dividing both sides by 2y, we get dy dx is equal to 2x over 2y. Well, I guess these 2's will cancel out nicely. So we have dy dx is equal to x over y. Number 5 says, find the coordinates where the curve has a horizontal tangent line. A horizontal tangent line means the slope is 0, which means that dy dx must equal 0. So in this particular case, that means that x over y must equal 0, but the only way a fraction is going to equal 0 is if the numerator equals 0. So this implies that x is equal to 0. So that's the x coordinate. To find the y coordinate, we need to substitute this back into the original equation. So that's just going to give us 0 plus y squared is equal to 1. We can ignore the 0, so taking the square root of both sides, we get y is equal to plus or minus 1. Don't forget that plus or minus, guys. So if we match these up, the two ordered pairs that we have will be 0, comma, positive 1 and 0, comma, negative 1. There's your plus or minus right there. So these are the coordinates where the curve has a horizontal tangent line. Number 6, determine whether the points you found in number 5 are the location of the relative min, relative max, or neither. When the first derivative is in terms of x and y like this, your best bet is probably to do the second derivative test. So let's take the derivative again and see what happens. We're going to have to use the quotient rule. Let me remind you of the quotient rule poem. As I'm reading this poem, remember that d means derivative of. So low d high, less high d low. Then draw the line, and down below, the bottom squared will go. So low d high. Low means just write down y. And then d high means multiply by the derivative of x, which is just 1, which we didn't really need to write down. But that's low d high, less means subtraction. less high d low. So high is x, and d low is the derivative of y, so dy dx. So low d high less high d low. Then draw the line, and down below, the bottom squared will go. So this is the second derivative. But we already know an expression for dy dx. It's x over y. So let's make that substitution. We will have y minus x times x over y divided by y squared. Of course, x times x over y will just be x squared over y. So I'm going to change that. To do the second derivative test, we need to evaluate the second derivative at each of the points that we found back in problem number 5. So let's start by substituting 0 for all of the x's and 1 for all of the y's. So we end up with this. But 0 squared is just 0, so this entire term is gone. So it's really just 1 over 1 squared, which is 1 over 1, which is positive 1. Now let's do the same thing for 0 comma negative 1. So I'm going to put in 0 for all of the x's, well there's only 1, and we will put negative 1 for all of the y's. Analyze this. Well, we still have 0 squared in the numerator. So this entire fraction is really just 0, so this is gone. So we have negative 1 divided by positive 1. This goes positive when you square it. Negative 1 divided by positive 1 is negative 1. So how does this tell us whether or not we have a relative max or a relative min? Remember, back on problem number 5, when we found these two coordinates, we were finding the points where the curve has a horizontal tangent line. So we know there is a horizontal tangent line at each of these points. But there are 3 ways you can have a horizontal tangent line. If the curve is concave down, then the point of tangency is a relative max. If the curve is concave up, then the point of tangency is a relative min. If the curve is neither concave up nor concave down, in other words, if there's a point of inflection, then that's going to be neither a max nor a min. Hopefully you memorized this chart a long time ago. If not, you need to pause the video right now and memorize it. I recommend that you write this chart in the margin before you begin your next test or quiz. So if the second derivative is positive, that means the original function is concave up. If f double prime is negative, that means the original function is concave down. We just discovered that for the point 0, 1, the second derivative is positive. That means the original function is concave up at 0, 1. And at 0, negative 1, the second derivative was negative, which means that the original function is concave down. That means 0, 1 is a relative min, while 0, negative 1 is a relative max. One more thing. When it said JYA, did you know that meant justify your answer? So let's summarize our answer with a justification. The graph of negative x squared plus y squared equals 1 has a relative minimum at 0, 1 because the first derivative is equal to 0 and the second derivative is positive. Notice that even though we are doing the second derivative test, you actually have to mention both the first derivative and the second derivative in your justification. dy dx equals 0 tells us that we have a horizontal tangent line at that point. And then the second derivative being positive tells us whether it's concave up or concave down, which indicates whether it is a min or a max. Similarly, for the second point, we say the graph of negative x squared plus y squared equals 1 has a relative maximum at 0, negative 1 because the first derivative is equal to 0 and the second derivative is negative. Notice I'm using this sort of awkward description, the graph of negative x squared plus y squared equals 1. That's because you should never use a vague term like the graph or the function. So I had to be specific. If I had a name like f of x, I would just say that. But since all we have is an equation, I had to say the graph of negative x squared plus y squared equals 1.